We're going to use matrix algebra to solve this system of equations here. It's the same example that we used in topic 1. Our first step is to set this out in the format AX equals D, with A being our matrix of coefficients, X being our column vector of solution values, and D our column vector of constants. So, looking at all our equations, we start with matrix A, and that will include all the coefficients: minus 11, 1, 1, 1, minus 6, 2, 1, minus 6, 2, 1, 2, minus 7, 1, 2, minus 7. X, as I said, is our column vector of solution values. So we will have, in this case, we've got P1, P2, and P3, which are the variables that we will be solving for. And then finally, we have our column vector of constants. So we've now set it out in this format, AX equals D. Our next step is to determine the value of the determinant and make sure that it doesn't equal 0. If it doesn't equal 0, then an inverse exists for matrix A, and we can solve for this system of equations. So with this being a 3 by 3 matrix, we're going to use the Laplace expansion to calculate the determinant, to find the determinant of matrix A. And we can calculate the determinant by using the Laplace expansion of any row and any column. So we can just choose. So if we decide to choose the first row to calculate the determinant, which we denote as follows. By the Laplace expansion, recall that we have to multiply all the elements in our chosen row, so these elements here, by their cofactors. So, starting with the first element, minus 11, recall to find a cofactor, it is equal to the minor of that element, and all that may change is the sign. And for example, the minor of this element here we would find by effectively eliminating that column and that row, and whatever is left over would be the minor. So if we write that down, so in terms of the cofactor, all that will change, or possibly change, going from the minor to the cofactor, is the sign. And whether or not the sign changes depends on the subscript of each element. So for example, this element here is in the first row, 1, and the first column, 1, of this matrix. So if we add 1 plus 1, we get an even number. We would get 2. And whenever the numbers in the subscript add up to an even number, the sign of the cofactor and the sign of the minor are the same. So in this case, there will not be any changes to the sign. So if we move on now to the next element in this row, which is now the element in the first row, 1, and the second column, 2. So 1 plus 2 equals 3, which is obviously now an odd number, which tells us that the cofactor of this element will take on a different sign to the minor. So in this case, the sign of the minor would be positive, because this is plus 1, so we would need to change that to a negative, as we are working with the cofactor as we calculate this determinant. So if we write down the element, minus 1, and now multiply by the cofactor, and we effectively, so we're working with this element here, we have to eliminate the first row, second column, and whatever is left over, effectively, we can write down. Okay, so finally we need to work with this element here, because we are doing the Laplace expansion using the first row here. And this now is the element in the first row, so we would have 1 here, and the third column of the A matrix. So 1 plus 3 is 4, which is an even number, which tells us that our sign would not change for our cofactor. So we would use the sign as it exists there, and working out the values to include, we would effectively eliminate that row and that column, and the values that are left over are as follows. Okay, then it's just a case of working through this calculation. Okay, remember now to calculate the value here, which is effectively a determinant here. Minus 6 times minus 7, and we get 42. Minus 2 times 2 is 4. Minus 1, 1 times minus 7, minus 1 times 2. Plus 1 times 2, minus 1 times minus 6. So we have here minus 6. Okay. 11 times 38. Minus, we got 1 here. 9 plus 2 plus 6 plus 8. So plus 4, 9, 8 plus 9 8, which effectively gives us minus 401. And we can see here that the value of the determinant is not 0, which suggests that, well, it tells us that an inverse exists for this matrix here, and we can go ahead and calculate the unique solution values of P1, P2, and P3. So to show that we can calculate the determinant of A using the Laplace expansion of any row or any column of this matrix here, I've included a second calculation of the determinant here, which uses the second column. Okay, so I've written it out, but we can work through the values. So starting with this element here, which is in the first row and the second column, so it would be 1 plus 2, which gives us an odd number, which tells us the cofactor will have the opposite sign to the minor. So instead of a plus sign, what we need to do is write down a minus sign, and then we have the value of that element, which is 1, and then by deleting that column, that row, we are left with 1, 2, 1, minus 7. 1, 2, 1, minus 7. Okay. So the next element in this column is minus 6, and this element, if we think of it subscripts, it's in the second row, second column. 2 plus 2 is 4. which is an even number, which tells us that the sign of the minor and the cofactor will be the same. So we don't need to change the sign here. We are working with a minus 6, and then we need to delete that column, that row. We're left with minus 11, 1, 1, minus 7. Minus 11, 1, 1, minus 7. The final element is this one here, 2, which is in the third row, second column. 3 plus 2 is 5, which gives us a odd number. So we're going to need to change the sign, going from the minor to the cofactor. And here we have a positive sign, so we need to change that to a negative. The value of the element is 2, and then deleting that column, that row, we're left with minus 11, 1, 1, and 2. Minus 11, 1, 1, and 2. So to work out the value of the determinant, what we have is the elements in the chosen row or column times by their cofactor. Okay, and then as we did with this calculation here, one merely needs to calculate these values, remembering that these are effectively sub-determinants of A, and we would work them out as follows. And working through this calculation, we get the same value for the determinant, minus 401, which, whether we use the first row or the second column, we can see that the value is not 0. So we know that this matrix is non-singular, and we know that a unique inverse exists for this matrix. So before continuing with our calculations, let's just remember what we are working towards. If we go back to our set of equations set out in matrix form, where we have AX equal to D, I've written that out here. So A being the matrix of coefficients, X being the column vector of solution values, and D being the column vector of constants. If we pre-multiply both of these sides by the inverse of matrix A, so we do that to both of the sides, we know that when we multiply a matrix by its inverse, then the product of that is an identity matrix. And in matrix algebra, an identity matrix plays a similar role to the role of the value 1 in scalar algebra. So we end up with X equal to the inverse of matrix A times by column vector D. So in other words, we can solve for the variables, the values of P1, P2, and P3 by calculating the inverse of matrix A, the inverse of that, and then multiplying it by this column vector D here. The next step in our calculation is to write down the matrix of minors. So if we give ourselves some space. Alright, so we are working with matrix A here, and we want to write out the matrix of minors. And it's a fairly simple exercise, but can take a fair amount of time. We need to take each element, for example starting with this element here, delete the corresponding row and column, and write down what we have left, and that there is the minor for that element there. Okay, moving on to this element here, delete that row and the column, and we write out -7. Okay, moving on to this element here, delete this column, row, we left with 1, -6, 1 and 2. Okay, this element, delete the column, delete the row, 1, 1, 2, -7, -7. This element, column, delete the row, -11, 1, 1, -7. Element, delete the row, column, we are left with 2. This element, the column and the row, 1, 1, -6, 2. This element, delete the row, delete the column, we left with -11, 1, 1 and 2. Lastly, this element here, delete the column and the row, we left with -11, 1, 1 and -6. So the next thing we need to do is calculate the values of each of these subdeterminants here, and I've set this out for you in the next 2 steps. For example, if we take this determinant here, -6 times -7 gives us 42, -2 times 4 gives us 4, and 42 minus 4 gives us 38. And so we can continue to work out all of these values, okay, etc. So I'll leave you to work through these calculations, and you will get the matrix of minors, which in this example here works out to this matrix here. Alright, the next part of the calculation is to convert these minors, to cofactors, and remember, all that's required in certain instances is a change of the sign. So if we then convert to cofactors, remember we have to look at the value of the subscripts for each minor here, and if we add them up, if they give us an even number, then the sign of the cofactor will be the same. So in this case here, for this minor here, it's in the first row, first column. 1 plus 1 is 2, so the sign will not change. The value of the cofactor is 38. For this minor here, we're looking at the first row, second column. 1 plus 2 is 3, which gives us an odd number, hence the sign on the cofactor will be different from the sign on the minor. So here it's a negative, so we're going to have a positive, so we'll end up with 9. This element, first row, third column, 1 plus 3 equals 4, which is an even number, hence the sign will not change. And so we continue. Second row, first column, 2 plus 1 is 3, odd number, the sign will change. Second row, second column, 2 plus 2 is 4, even number, the sign stays the same. Second row, third column, 2 plus 3 is 5, odd number, the sign will change. Third row, first column, 3 plus 1 is 4, even number, the sign stays the same. Third row, second column, 3 plus 2 is 5, odd number, sign changes. And lastly, third row, third column, 3 plus 3 is 6, even number, the sign stays the same. Okay, our next step now is to find the transpose of this matrix here. And remember, what happens for the transpose is the first row becomes the first column in the transposed matrix. Second row becomes the second column, third row becomes the third column. So basically the rows and the columns switch around. So we can now write out the inverse of matrix A. It's 1 over the determinant, which remember we calculated previously as negative 401, times by this matrix here. Okay, so this here is the inverse of matrix A. If we recall how we're going to solve for this system of equations, we have our column vector of solution values, our variables P1, P2, P3, equal to the inverse of matrix A times by the column vector of constants. Okay, so here we have our inverse, okay, which we've just calculated, and our column vector of constants. This matrix here, which is the transpose of the matrix of cofactors, is also known as the adjoint of matrix A. Alright, so we now need to work through this calculation, and a good starting point is to multiply this matrix by this matrix here. So we need to see, are they conformable for multiplication? And we can see that they are, because the number of columns in the lead matrix is 3, the number of rows in the lag matrix is also 3. So those are equal. And we also know what the dimension of the product matrix will be. It will be the same number of rows as the lead, so there will be 3 rows, and the same number of columns as the lag matrix, so there will be 1 column. So we can set that all out if we just leave that value as is, and we set out what the product matrix here will look like. We've said it's going to have 3 rows and 1 column. Okay. And if we work through this calculation here, okay, we have to take each element from the row, the first row of the lead matrix, and multiply it by each element in the first column of the lag matrix. Okay, and then sum all those products together. So 38 times by minus 31 plus 9 plus minus 26. Minus 24. Okay, then we move on to the second row of the lead matrix times by the first column of the lag matrix. And we get 9 minus 1, 76, 26, 23 minus 24. And lastly, we move on to the third row and the first column. Continuing with our calculation, right, so if we just work out minus 2, 1. Alright, so we are nearly there. Okay, we now just sum these, or subtract them rather. That minus that minus that, we end up with minus 1604. 7. So, 6. Okay, so we're nearly at the end now. All that remains to be done is effectively multiply each of these elements here by this value here, and what we end up with is V1, V2, V3, which is our column vector of solution values, column vector x, and if we work these all out, we're going to end up with minus 1604 divided by minus 401. We'll get a value of 4 minus 2807 divided by minus 401, we're going to get a value of 7 minus 2406 divided by minus 401, we get a value of 6, and these here are our values for P1, P2 and P3. And if you go back to the example we worked through in topic 1, you'll see we got the exact same answer.